The binomial theorem. Before we look at the binomial theorem, let's define the binomial coefficient. The expression, which looks like elongated parentheses with a number n on the top and a number r on the bottom, read out loud as n choose r, is called a binomial coefficient, and it's defined by the following formula. So we might see it as, again, elongated parentheses with a number on top n and a number on the bottom r, or we might also see NCR, again read as n choose r. In either case, the answer to this is a number found by using the following formula. So we have n factorial in the numerator, and we have all over. In the denominator, we have r factorial times the quantity n minus r factorial. So the answer is just going to be a number found by using this formula here. So substituting n in here, and here, and r in here, and here, and then simplifying. It is helpful to remember that if you're doing n choose n, so if you have the same number on the top and on the bottom, or if you're doing n choose 0, that the answer to that is just going to be 1. So you can always apply this formula, but it's going to be helpful to remember this. N choose n or n choose 0 always gives us 1. And then if we're doing n choose 1 or n choose n minus 1, so if you have a number and then 1 less than the number below it, the answer to that is always just n, so the number on top. So these are just little shortcuts, but we can always just plug in n and r into this formula to find our binomial coefficients. Let's do a few quick examples. We want to evaluate each of these binomial coefficients. So here we have 6 choose 2. So the formula says that the number on top, 6, is going to go in the numerator as 6 factorial. Then the number on the bottom, 2, is going to go in the denominator as 2 factorial. Then we subtract 6 minus 2, which is 4, and that's also going to go in the denominator next to the 2 factorial. And from here, we're going to go ahead and simplify. So let's remember how factorials work. 6 factorial is 6 times 4 times 3 times 2 times 1. So 6 times 5 times 4 times 3 times 2 times 1. Now I'm going to choose to just stop at 4 factorial because that's 4 times 3 times 2 times 1. And I can see there's a 4 factorial in the denominator. So I'm going to leave the top as 6 times 5 times 4 factorial. On the bottom, I have 2 times 1 times 4 factorial. So the 4 factorials are going to cancel because it's just 4 times 3 times 2 times 1 on the top and on the bottom. So those are going to go ahead and cancel out. So what I have left is 6 times 5 over 2 times 1, or just 30 over 2. So that's going to give me 15. So all of these should be numerical answers. The binomial coefficient gives us a coefficient, which is just a number. Now let's go ahead and try the next one. So we have 4 choose 4 here. So we're going to go ahead and put 4 factorial on the top, 4 factorial on the bottom, and then we're going to subtract 4 minus 4. So we'd also get a 0 factorial on the bottom. So the 4 factorials are going to cancel out. That's just 4, 3, 2, 1 multiplied, and 4, 3, 2, 1 multiplied. So those are going to cancel. So I have just a 1 on the top. And then here, 0 factorial by definition is 1. So I really just have 1 divided by 1 here, which is 1. And this was that shortcut I mentioned just a minute ago. If you have n over n, so if you have the same number over the same number, then the answer to the coefficient is just going to be 1. Same thing if you have n over 0, then the answer is just going to be 1. And here we have 4 choose 1. So we're going to have 4 factorial in the numerator, 1 factorial in the denominator, and then 4 minus 1 in the denominator, factorial, so that's 3 factorial. So we have on the top 4 times, let's just write this one all out, it's like 4 times 3 times 2 times 1. On the bottom, 1 factorial is just 1, and then we have 3 times 2 times 1. So the 3 times 2 times 1 on the top and on the bottom are going to cancel, because essentially that's 3 factorial, 3 factorial. That's why we canceled those out. So all we have left is 4 on the top, right? 4 over 1, so we just have 4. And again, that was that helpful tip to remember. If you're doing 4 or n, choose 1, then the answer is just going to be n. So here we have 4, choose 1, the answer is just going to be 4. The other part about that to remember is if you're doing n on the top and 1 less than that on the bottom, so let's say we were doing 4, choose 3, that's also going to be 4. That's also going to give us 4. So those are just some little helpful shortcuts to finding these binomial coefficients. Let's go ahead and remind ourselves of what a binomial expression is. A binomial expression is of the form the quantity a plus b to the nth power. So let's go ahead and look at a couple of binomial expressions. If we have a plus b all raised to the 0 power, that's just going to be 1. If we have a plus b raised to the first power, that's just a plus b. If we have quantity a plus b raised to the second power, then we have to start distributing. So a plus b times the quantity a plus b, if we multiply it all out, gives us a squared plus 2ab plus b squared. If we keep going, quantity a plus b cubed, that's quantity a plus b times a plus b times a plus b. It's a lot of distributing, and it simplifies to a cubed plus 3a squared b plus 3ab squared plus b cubed. And we can, of course, continue on. We see a plus b raised to the 4th and a plus b raised to the 5th. And we can see that it'd be a lot of distributing, and we'd end up with these quantities on the right-hand side. What I want to do is look at the coefficients for a second. So we just said a second ago the formula, or we reviewed the formula for finding a binomial coefficient. So let's just look at the coefficients of the expanded binomial expressions here. So for the second one, a plus b to the first, I'm going to go ahead and write the coefficients. Those are just 1s. And then on the next one, I'm going to put the coefficients 1, then we can see 2, 1. And then here we have 1, 3, 3, 1. And then we have 1, 4, 6, 4, 1. And then down here we have 1, 5, 10, 10, 5, 1. So just looking at the coefficients here, I want to try to see a little bit of pattern. So I went ahead and extracted all of those coefficients, and it created what's called Pascal's triangle. So the coefficients of the binomial expansions here form what's called Pascal's triangle, and there's a lot of pattern to be recognized here. First, the diagonals on the outside, they're all just 1. And then if I look at the next diagonal, I can see it goes down by whole numbers every time. So 1, 2, 3, 4, 5, and then here 1, 2, 3, 4, 5. It's kind of also another really cool pattern to recognize, that if you add any 2 coefficients along one row, the sum of those is going to give us the binomial coefficient in the next row that's like directly between the two. So 1 plus 2 is 3, and then 2 plus 1 is 3. And if I do 1 plus 3, I get 4. 3 plus 3, I get 6. So with that in mind, let's go ahead and write out what the next row of this would be, because it doesn't just stop at this row here. So the next row would be 1, and then 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, and then we always have 1s along those outside diagonals. So I now know the coefficients of the next polynomial that would arise from doing a plus b to the 5th, or excuse me, to the 6th. That's the next one. So all we'd be missing is the a and b and what powers those are raised to. But there are some patterns to that as well. So if we were interested in a plus b to the 6th power, Well, we can see that here the first term is always just the a variable to the power of the binomial, so a to the 6th. So let's go ahead and write that out. So it's going to be 1 and then a to the 6th. And now we know what the next coefficient is going to be. It's going to be 6. So we're going to have plus 6. And then now we can see there's a copy of a and a copy of b. So here I'm going to go ahead and put an a and a b, but let's talk about the powers. So in the next term, we can see that it goes down by 1. So we had a to the 5th, and now it's a to the 4th. When I'm doing a plus b quantity to the 4th, it was a to the 4th, then a to the 3rd. So it goes down by 1, and that pattern continues. So a to the 4th, a to the 3rd, a squared, a. So it's going down by 1 every time. So this is going to be 6a to the 5th. And since it's the first appearance of b, it's going to be b to the 1st power. So we can see that in the second term, it's the first time that the second piece of the binomial shows up, and it's to the 1st power. And then the power of b is going to go up by 1 every time. So this is going to be 6a to the 5th b, and then plus 15. We're going to grab the coefficient from Pascal's triangle. So we're going to have 15, and then a is going to drop to the 4th, but b is going to go up to the 2nd power. And then we're going to have 20a to the 3rd, b to the 3rd. So a went down by 1, b went up by 1, the exponent. And then 15a squared b to the 4th plus 6ab to the 5th. And then finally, in the last term, we lose the a. We lose the first term of the binomial. So we're just going to have plus b to the 6th. So we were able to find the expansion without multiplying it all out, which, if you can imagine, would take a lot of time to multiply quantity a plus b times quantity a plus b, etc., all the way up to the 6th power. So there's all of this pattern to notice from Pascal's triangle to grab those binomial coefficients. And then there's the pattern to recognize with the variables raised to the exponents. This finally brings us to the binomial theorem. So for any positive integer n, if we're trying to expand out the binomial quantity a plus b raised to the nth power, then instead of multiplying it all out, we could jump straight to the expansion. So to find the expansion, we are going to use the binomial coefficient formula, starting with n choose 0. So remember, n is what we're raising this to. So we're going to have n choose 0 as the first coefficient, n choose 1 as the second coefficient, n choose 2 as the third coefficient, and so on, all the way up until the last coefficient will be n choose n once we get to the same number on the top and the bottom. And then, in terms of the variables a and b in each term, it's going to follow that pattern that we just looked at, where a is going to start out raised to the nth power, and we're not going to have any b at all. Remember, b to the 0 is 1. So the first term's just going to have the first variable in it, a to the n, and then there's not going to be any b, because b to the 0 is 1. Then we're going to drop the power by 1 of a, and that's the first appearance of b to the 1st. Then we're going to drop the power of a again, and increase the power of b by 1. Drop the power of n again, n minus 3, increase the power of b by 1, all the way until the last term where there's no a's, a to the 0 is 1, and b, the second piece of the binomial, is finally raised to the nth power. So this will get us the expanded binomial without having to multiply it all out. In this example, let's go ahead and use the binomial theorem to expand the quantity 2x minus 3 all raised to the 5th power. So the first thing I'm going to go ahead and do is think about this as 2x plus negative 3 to the 5th, so that I can identify my a and b. So I have 2x is my a value, and negative 3 is my b value. So the binomial theorem was a plus b raised to the n. So the value of a is 2x, the value of b is negative 3. The value of n is 5. So let's go ahead and apply the binomial theorem and then simplify it. So to find the coefficients, we're going to use the formula for binomial coefficient. It looks like, remember, the elongated parentheses. So we're going to start with 5, and then it's going to be choose 0. And then we're going to have the first piece of the binomial raised to the 5th power. So we're going to have 2x raised to the 5th. We need to make sure and keep the first term in parentheses. So 2x to the 5th. And then the first term has no second piece of the binomial. So this would be like -3 to the 0, which is just 1. So we're not going to bother putting it. Then the second term of the binomial expansion is going to be 5 choose 1. Then we're going to have 2x in parentheses raised to the 4th. And then we're going to put the b term raised to the 1st power. So this is the first appearance of the second term in the binomial. And then we keep going. We're going to do 5 choose 2, 2x in parentheses to the 3rd, -3 squared. So the first term, the power decreases. The second one, the power increases. And we keep up with the pattern. 5 choose 3, 2x squared, -3 to the 3rd. We are going to run out of space, so because I can do this, I'm going to drop it down. Then we have 5 choose 4. We have 2x to the 1st, and then -3 to the 4th. I need even more space. And then finally we have plus 5 choose 5. We have just -3 to the 5th. So we're not going to have any more of the first piece, the 2x part, in the last term. And we know to stop because we've reached n choose n, the same number choose the same number. Alright, so now it's a matter of simplifying the binomial coefficients here, right, using the formula. And then just simplifying what we have left, multiplying things out. So here's where I was mentioning it's helpful to kind of know those shortcuts in terms of binomial coefficients. So what do we know about 5 choose 0 and 5 choose 5? Well, those are both 1. And the other way to kind of remember that is if you think about that Pascal's triangle, the outside values were always just 1. So we're going to go ahead and replace those, with 1s. So this is going to be 1, and then I have quantity 2x to the 5th, and then I'm going to go ahead and simplify this last term over here as well, because we know this has to be 1, and then quantity -3 to the 5th. Then we'll work on the next binomial coefficient, and because of that symmetry, we also know that the second to the last one is going to be the same value. And again, these were ones that were kind of under those helpful shortcuts. If you have n choose 1, or if you have n choose n minus 1, so 1 less than that, the answer is just going to be n, the number on top. So this is simply 5. So I have 5 and then times quantity 2x all to the 4th times -3. And then here, this is 5 times 2x times -3 all raised to the 4th. And so now all we need to do is find these coefficients, 5 choose 2 and 5 choose 3. And again, because of symmetry, they're going to end up being the same value. As I work from outside in, those are going to be the same values as I creep on inside. So I'm going to go ahead and apply the formula up here for finding the binomial coefficient. 5 choose 2, it was 5 factorial over 2 factorial times 3 factorial. The difference between 5 and 2 is 3. So here we have 5 times 4 times 3 times 2 times 1, which is 3 factorial. I'm going to keep that 3 factorial on the bottom because it's going to cancel out. And let's see, 2 factorial is actually just 2 times 1, so I'll just leave that as 2. And so I have 5 times 4, that's 20. 20 over 2 is 10. So this binomial coefficient is 10, as is this one here. So I have 10, and then times 2x cubed times -3 squared. And then here I have 10 times quantity 2x squared times -3 cubed. So we have 1, 5, 10, 10, 5, 1. And if you notice, those are the same values from Pascal's triangle. So if we had recreated Pascal's triangle, we could have put the coefficients in from that instead of using this formula for n choose r, right? The formula for finding the binomial coefficients. But, I mean, that's only going to work if we have kind of a smaller power that we're raising the binomial to. The larger this becomes, the less likely you're going to want to create a gigantic Pascal's triangle. So now let's go ahead and just kind of clean this up and simplify it. So quantity 2x to the fifth, well 2 to the fifth is 32, so we're looking at 32x to the fifth, and then we're going to have minus overall, because here we're going to have negative 3 times 5, and then we're going to have 2 to the fourth, so 2 to the fourth is 16, and 16 times 15 is 240, so we're going to have negative 240 x to the fourth. The next term is going to be positive because we're going to have negative 3 quantity squared, that's 9. And then 9 times 10 is 90. And then we're going to have 2 cubed, that's 8. So 90 times 8 is 720. So plus 720 x cubed. The next term will be negative because negative 3 to an odd power is going to be negative. So we're going to have negative, let's see, 3 cubed is 27, and so we have 27 times 10, so 270, and then times 2 squared, that's 4, so 270 times 4, 540, 1080, so we have 1080 x squared, because we had x squared, and then here we have 2 times 5, that's just 10, times negative 3 to the fourth, that's going to give me 81. So 81 times 10 is 810, and then just one copy of x. And then finally we have negative 3 to the fifth, that's going to end up staying negative, and 3 to the fifth is 243. So here is my binomial expansion of quantity 2x minus 3 to the fifth. So it does, seem like a lot of work, but if you think about the work that it would take to multiply all of this out if you expanded it, this is actually a lot shorter. Now in this next example, we're not going to find the entire expansion. We're simply asked to find the coefficient of x to the seventh in the expansion of quantity x plus 2 to the 9th power. So the idea isn't to do the entire binomial expansion and then just look at what's the coefficient of x to the seventh. So we actually want to make shorter work of this, right? So what we want to go ahead and do is think about how if we did have x plus 2 to the 9th, the first term would have the x to the 9th in it, right? So we'd have the first term is x to the 9th, and the coefficient in front would be 1. And then the second term would have an x to the 8th in it. So we'd have that x to the 8th, and we'd have 2 to the first power. And then the coefficient in front would be found by doing 9 choose 1. Because remember, the first one is n choose 0, 9 choose 0, which is always 1. And then here it's going to be 9 choose 1. And then the next one is going to be 9 choose 2, and then we have x to the 7th 2 squared. So if we want the coefficient of x to the 7th, we both need to find 9 choose 2 and multiply it to 2 squared, because the total coefficient, right, would be those two things multiplied together. So we're going to need to go ahead and find 9 choose 2 and then multiply it to 4. So let's go ahead and do that scratch work on 9 choose 2. It's going to be 9 factorial over 2 factorial times 7 factorial, the difference between 9 and 2. And here I'm going to go ahead and start putting 9 times 8 times 7 factorial. I'm going to stop at 7 because there's a 7 on the bottom with a factorial. So we have 2 times 7 factorial. Those are going to cancel. And here, we can cancel a 2 into 8 4 times, so 9 times 4 is 36. So 9 choose 2 is 36. Then we have x to the 7th times 4. right? So the coefficient of x to the 7th is going to be 36 times 4. So that's going to be 144 x to the 7th. So to find the coefficient is 144. Remember, the coefficient is the number in front of the variable, x to the 7th. So here, another pattern that I want us to recognize is that the exponents of the a and b are always going to add together to be the original n value. So here, x to the 8, 2 to the 1st. 8 plus 1 gives us 9. Here, x to the 7th, 2 squared. If I add those together, it's going to give me 9. Because if I drop by 1 every time and go up by 1 every time on the first and second piece, those are constantly going to keep having the same sum. Right? Those are going to have the same sum every time. Something else that I want us to just observe is that the coefficient, so we see 9 choose 2, notice the number on the bottom is the exponent of the second piece of the binomial. So here, 9 choose 1, the exponent of 2 is 1, that's on the bottom. Here, the exponent of 2 is 2, that's on the bottom of 9 choose 2. So we wouldn't actually have to write out, like we started writing out the first couple terms to get to the x to the 7th term, but we don't actually have to do that. So let's say we wanted to find the coefficient of x to the 5th. So I don't need to like keep going with this pattern here. I could just jump straight to, okay, if x to the 5th is involved, then that means that the second piece, 2, well, 2 would have to get raised to the 4th. Why does 2 have to get raised to the 4th? Because the two exponents have to add together to be 9. And then what's the coefficient in the front? Well, it's going to be 9 choose 4, right? So it's going to be 9 choose 4. And actually, technically, the bottom value could also be the other exponent. It doesn't matter because of that symmetry of like working outside in. So it's going to be 9 choose, honestly, either of these exponents will give us the correct binomial coefficient. So here, I could find the coefficient of x to the 5th without, having to go all the way down. I was just trying to show the different patterns that were happening. And in this example, we want to find the 4th term in the expansion of quantity 2x plus y squared all raised to the 11th. So here we want the 4th term in the expansion. Let's go ahead and start writing out at least what the first term and the second and third and fourth term would involve with just the x variable. We only need a little bit of information from the first few pieces. So in other words, the first term is going to look like 2x to the 11th, and the second term would be 2x all raised to the 10th, and then we'd have 2x all raised to the 9th, and 2x all raised to the 8th. So I'm just focusing on the first piece, 2x, and I'm decreasing the power by 1 every time. So thinking about first, second, third, the 4th term would have a 2x to the 8th involved. Now once I get to that piece, now I can just focus on the rest of what's going on with that one term. So we have 2x to the 8th. We're going to end up having the second piece of the binomial, so that's y squared. That's going to need to be raised to the 3rd power. So why the 3rd power? Because the exponents have to add up to 11. So 8 and 3 is 11. And then what's going to go in front? The coefficient in front is going to be 11 choose 3. Right? But really, it could be 11 choose 8 or 11 choose 3. It doesn't really matter, right? So now we're just going to need to find this value, 11 choose 3, and then multiply all of this out. It's going to be pretty big numbers going on. So 11 choose 3, let's do that scratch work over here. So we're going to have 11 factorial over 3 factorial times 8 factorial. And this kind of shows you why you can choose either 3 or 8, because notice if there's an 8 on the bottom, then 11 minus 8 gives you 3. So either way, you're going to have a 3 factorial and an 8 factorial on the bottom. So let's simplify this thing. We get 11 times 10 times 9 times 8 factorials, where I will stop to cancel with the 8 factorial on the bottom. And I'll expand the 3 factorial. So I mean, you might end up thinking like, oh, these are going to end up being really big numbers, but there's a lot of canceling and simplifying that you can do. So like 2 goes into 10 5 times, 3 goes into 9 3 times here. So we're going to end up having just on the top 11 times 5, so 55 times 3, so that's 165. So I mean, not terrible when you start to think about how big these numbers could get. So 11 choose 3, is 165. And then we are going to have to multiply that by, let's see, 2 to the 8th times x to the 8th. So 2 to the 8th is 256. And then we have times x to the 8th. And then here, let's remember, if you have y squared to the 3rd, these multiply together. So we're going to have y to the 6th. And now we do have to multiply 165 times 256, and that ends up being 42,240. Then we have x to the 8th, y to the 6th. So this is the 4th term in the expansion of this binomial. So it did take a little bit of work, but definitely not as much as it would take to expand this whole thing out and then just look at that 4th term in the standard form of the answer.